We are live. Welcome back. Today, we're going to go a little off the cuff. We're not going to talk about anything that's within the book. Last time, we talked a lot about leaving groups, conjugate bases, acid-base reactions, blah, 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 blah. I feel like it is appropriate to have a short discussion about resonance and factors that contribute to conjugate base stability because it is such a big thing in the field of organic chemistry. So to begin, let's have a discussion about resonance. So resonance is basically defined as the delocalization of electrons through a p-orbital system. And specifically, this is a conjugated p-orbital system, right? And what does it mean for a p-orbital system to be conjugated? This is one of those terms that's better in a diagram as a definition than it is in words. This is not a conjugated system. This is called a cumulated system. Accumulated system, where you have a p-orbital like this that binds to a p-orbital like this, and then you have one here that goes like this and bonds to one like this. And you have another one here that goes like this and bonds to one like this, right? That is called a cumulated system, right? And ironically enough, resonance can't really occur through cumulated systems, right? But they can occur through conjugated systems. So what would a conjugated system look like? It would look something like this. Where those p orbitals only attach to one that's directly next to it. And your sp2 carbons are kind of staggered. Because you realize in the cumulated system I just showed you, in this example, yeah, those end carbons are sp2, but what about those carbons in the middle? Are those sp2? No, they're not, right? Because they have how many electron domains? 1, 2. And remember, do my trick. You throw down 4 letters. You're using 1, 2. That means the hybridization there is sp. And you have 2 free p orbitals. What are those p orbitals doing? Well, one of them is attaching to this carbon to the left, and the other one is attaching to the carbon to the right. Correct? Whereas if you look at the conjugated system, right, I drew out the p orbital map just so you can visualize it. But if you look at the conjugated system, you've got sp2 and sp2 and sp2 and sp2 and sp2 all the way through. So now that you are good at identifying sp2 carbons, sp2 hybridized carbons, and understand, remember, we have what? sp, p, p. So all those have that lone p orbital, which we display in the p orbital map, right? You should be able to almost see this p orbital map in your head. You should almost be able to visualize it when you look at a diagram like that, right? Okay. So, that being said, if you can see this and you can see that, you can merge the pictures and understand that conjugated systems are basically just lines of sp2 carbons or sp2 atoms in general, right? And in real life, what do electrons do? Electrons move through what? Electrons move through wires, right? And I want you to think of conjugated systems like wires, like little wires that connect parts of the molecule together, that electrons are capable of moving through. Is that jacket from Uniqlo? I love Uniqlo. These pants are from Uniqlo. And so is this shirt. The whole outfit's from Uniqlo. And my hat. So, you see this, and now we're going to build on that understanding. So we know that electrons can move through conjugated systems of p orbitals, lines of sp2 atoms, correct? But the electrons don't really want to move here. There's no reason for them to do so, so they don't really do it. When would they do it? It's when there's a disturbance inside of the molecule, when there's a problem, right? And resonance is really sweet, because it's the molecule basically giving up a part of its stability somewhere else for the sake of the whole molecule. It's a part of the molecule giving itself up for the rest, right? It's like one big family, right? So let's take a look at a conjugated system that looks like this. We have an electron deficient region in this molecule, right? And I want you to ask yourself, in your head, can you make a p orbital map of this molecule? Can you look at it and think, where are my p orbitals? Right? So so first we have to figure out what's our hybridization everywhere. And if you're not at the level to figure out hybridization by looking at that yet, let's dumb it down even further. This is inherently what we're looking at, correct? That's what we're looking at. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Positive charge on 5. Double bonds between 1, 2, and 3, 4. Right? This is what we're looking at. So now you'll be able to tell me, oops, hold on. 1, 2, 3, 4, 4, 4. There we go. It's been a minute since I did that. I usually just draw them out like this. So now you'll be able to tell me exactly what is the hybridization of all these carbons. Let's do this one. We got 1, 2, 3, it's sp2. Over here, you got 1, 2, 3, that's sp2. And over here, it's sp2. And over here, it's sp2. And the carbocation. The carbocation. What are all carbocations? All carbocations are sp2. And if it is sp2, that means the carbocation has what? It has a free p orbital. Has a free p orbital. So this has a p orbital, and that has a p orbital, so does that, and so does that, and so does that. And one for each of them. And that makes this system of p orbitals what? Conjugated or accumulated? Conjugated. Very good. It's conjugated. Right? So that's number one. Electrons move through wires, or p orbital systems. Specifically conjugated p orbital systems. Number two, p orbitals are what? P orbitals are, I said it last week, p orbitals are electronegative. P orbitals are electronegative. Right? One more thing. In this molecule right here that I drew over, right? Can you guys tell me the geometry at each position of those carbons? What's the molecular geometry there? If it's sp2, it's trigonoplanar, right? We're going to come back to that later, that trigonoplanarity of an sp2 atom, because it's very important in biochemistry. Well, it's important everywhere, but it's particularly important to us in biochemistry. Right? P orbitals are electronegative. So if you can imagine, these p orbitals over here and this p orbital over here, they're fighting for the electrons, right? And this one, since this p orbital is pulling on the electrons and it has a positive charge, you want to donate to that positive charge, don't you? You want to donate some electron density to the positive charge. And the fantastic thing about conjugated systems is that they don't just donate. They don't just let someone borrow, they give. They completely donate. So what happens is that these electrons move through the wire. They go right here, look, electrons right here. The wire connects these portions, the electrons move through the wire. It's like this, and it folds over that way, right? So if we draw our resonance brackets I'm going to do it properly. I'm going to show you guys how to do this properly because I always want you to use a proper notation. You drop a bracket. Whenever you're doing resonance, it happens inside of brackets. You use a double-headed arrow to move 2 electrons. You give resonance arrows, and you show what changed and what didn't. So none of this changed, none of the backbone changed. We have a bond here now, and the positive charge moved over there. Good? Yes. And then what else can happen? Because remember that when you're inside the resonance brackets, everything's frozen. So now this can bend over that way, right? So we can get resonance that goes like this. And that's how you know I've been doing orgo for a long time, when my bonds overlap like that, because I'm just too lazy to draw them properly. Because a lot of people will say, hey, Yusuf, this and that are the same thing. But no, they're not. If you freeze the molecule in place. These brackets freeze the molecule in place. And what I'm saying to you by drawing this is that the positive charge is shared between positions 1, 3, and 5 on this molecule in free space. When it exists as a hybrid of all 3 of those structures. And the question we have to ask ourselves is, which of those 3 structures does it look the most like, and which of those 3 structures does it look the least like? Those are called major and minor contributors. Who can tell me what the major contributor is here?
First one?
This one?
Yeah.
Why? How does it make it different than that one?
Actually, second one.
Why the second one?
Because it's in between two. Because in between two carbons.
So, donate to the poor, steal from the rich. Robin Hood. Organic chemistry is very Robin Hood. What do we mean by the poor or the rich? The electron poor and the electron rich. Is a carbocation electron poor or electron rich? It is electron poor, right? Here's your next rule. R groups are donating groups. R groups are donating groups. What's the opposite of a donating group?
Givers.
A withdrawing group. Donating groups and withdrawing groups. So R groups are donating groups. And if R groups are donating groups, let's take a look at what's donating here. So this is an R group, right? This whole thing. So that is donating to there, right? I'm going to draw it like this without the thing. So that's donating that way. Here, we have an R group to the left and an R group to the right. That means we're donating this way and this way. And here, we're donating this way, correct? So what's better? 2 people donating to the poor or 1 person donating to the poor? 2 people. So this has the most stability, which means this is your major contributor.
In other words, it's in between of 2 double bonds. That's why it's major.
Not 2 double bonds, but 2 R groups in general, right? In the same sense that this carbocation is better than this carbocation. Better. Because what's donating here? Donate, donate, donate. 3, 2. Which would be better than 1, right? Yeah, you had a question or what?
No, so whichever one has more to steal from is the most stable.
Exactly. So that's the major contributor, which would make these the minor contributors. Now, we have to differentiate. If one of them is minor and another one's worse than that, that last one becomes negligible, right? But these look the same, so they are equally minor. So this is minor, and this is minor. So this might be 70% of the structure, and this might be 15, and this might be 15. So what does the true structure look like? It looks like a hybrid between all of these, where the majority of the positive charge is held in the center of the molecule. So if this molecule were to undergo a reaction, if this molecule, which is also like, it's actually it looks kind of like that, right? Plus 0.7, plus 0.15, plus 0.15. If that were to undergo a reaction with a nucleophile, the nucleophile would preferentially attack carbon 3. Carbon 3. Because it has what? It has what we call the most carbocation quality. Carbocation quality. The carbocation quality of carbon 3 is the most, well, it has the most, yeah. So the carbocation quality is highest in carbon 3. Does that make sense? Very good. Okay. So let's do one that's a little more complicated than that. Okay? Can you draw a p-orbital map? I'm sure you can. sp2, sp2, sp2. We've got 3 atoms which can contribute to the resonance, right? We've got the wire moving. Where's our wire? We've got our wire moving like this, right? That's our wire, just those 3. So this right side of the molecule is completely isolated from the wire. So it's not going to communicate. It's not going to participate in the resonance. So resonance can go this way. And a lot of people don't realize it, but even though it doesn't happen that much, resonance can also go that way. Yep. So now we're getting into lone pair resonance. And it's always better to have something with an octet than something without an octet. So this is the major contributor. But what do minor contributors do? Minor contributors tell you the site of attack on a specific molecule. Will you be asked the difference between these two? Not really, because it's like if you're here, it can resonate, but it doesn't donate as much because this is withdrawing. The BR is withdrawing. That's another thing. Halides / electronegative atoms are withdrawing. That's another thing. But then if you're here, it's like you get the secondary and you're next to 2 positions and it donates. So that's going to be quite difficult. You're not going to get a question like that. But I just wanted to show you that lone pairs off of other atoms can donate as well. What does this mean for reactions? So we're just doing carbocations because carbocations are the easier ones to understand. And then we're going to do carbanions because carbanions are going to land us into a discussion about conjugate bases and base stability. Because what are negative things? Negative things are nucleophiles or bases, right? So let's get through this first and then we'll move on. So what does that look like inside of, like a reaction? Well, we see it all the time. I want you to tell me what happens there. It's an SN1 reaction, right? It's an SN1 reaction. Why isn't it E1? Well, I didn't put a lot of heat in the flask. So at lower temperatures, SN1 predominates, and at higher temperatures, E1 predominates, right? So if we're going to get an SN1 reaction like that, let's take a look at what happens. Can I erase this? Cool. Am I writing big enough? Can you guys read properly? Okay. Huh? You're used to it? Yeah, I know. I'm also used to writing small. All right, so let's take a look at what happens here. So we got a bromine And we got that group right there. Right? Can anyone already tell where I'm going with this? If you can, you have really good foresight. Because I know where I'm going with this. Right? Let's put this in a solution of water, and let's let the reaction go. The first step of every SN1 reaction is the leaving group fucks off, right? The leaving group leaves. And we get the slow step, which is the formation of the carbocation. Right? And organic chemistry students who learned SN1 will hop on this bandwagon and go, hey, I know what happens. Everyone put your pens down. Everyone, pens down. I know what happens. H2O comes here, and we get two products, one of which is the R enantiomer, and one of which is the S enantiomer.
So it's going to be racemic mixture because they have different.
It's a mix, right? So then when we deprotonate both of these, we get that. And that looks like a perfectly good answer until your professor marks you wrong and tells you that this is a very, very, very minor product. Incredibly minor product. But professor, I showed all my work. It's right there. The leaving group leaves and we get the carbocation and it attaches and we go. What's wrong here? Do you guys remember? It's a very small fact about organic chemistry that's easy to forget. Whenever you make a carbocation, the carbocation is greedy. It is greedy to be in a better position than it is now. And remember that the molecule will sacrifice itself to save the carbocation. If there is a hydrogen next to the carbocation on, good timing. If there is a hydrogen on the molecule adjacent to a carbocation, and that hydrogen is on a position that is either more substituted or more stable than the position that the carbocation is currently on, you will get what's called a hydride shift or a proton transfer. It is more commonly called a hydride shift. And this hydride shift is an intramolecular movement of this hydrogen to stabilize the carbocation in two ways. Number one, to get the positive charge off of the less stable position and move it onto the more stable position. So we get that. And that is why your organic chemistry professor marked you wrong when you put this as the answer. Because that doesn't happen. At least not the majority, maybe 1-2%. 90+% of the solution, the carbocation turns directly into that. Why? Why? Because remember, we're in terms of delta H, in terms of energy, we're trying to go down, right? That first carbocation has an energy up here. The moment it sees that hydrogen, it can snap it and drop it down here. So if it goes down in energy and becomes more stable, that's better, and that will happen. And that contributes to what? So the negative delta H here also contributes more to a negative delta G. Anything to make the delta G more negative. Anything. Anything for the delta G. Thermodynamics. It's all thermodynamics and acid-base reactions and thermodynamics. It's all you have to know, right? So that hydride shift stabilizes the carbocation. How? By the ways that we spoke about before. Because here you have 1, 2 donors. Here you have 1, 2, 3 donors. It is also very good etiquette to show your hydrogen after it is shifted. It is very good etiquette, and your organic chemistry professor will love you for it. Because you make it easy to show you know where things are going.
It's beta hydrogen, right?
Huh?
Or I'm wrong. Is it beta hydrogen, right? It's called beta hydrogen.
Yeah, so this would be an alpha hydrogen, because that's the carbocation position. We'll talk about like alpha beta when we get to later in orgo. Because we're going to have to do like aldol reactions and Claisen reactions, et cetera, et cetera.
Just the point that says R groups are
Donating groups. And halide / electronegative atoms are withdrawing. So that is a more stable carbocation. And if it's more stable, that's the one that's going to move forward. Do you guys mind if I make this concise and I just say minus H plus? Attaches, retract the H plus, right? Do I need to put plus minus there? Is that chiral?
Yes.
Where? It is not chiral because this has an ethyl group, an OH group, and 2 methyl groups. It is not chiral. Does that make sense? Carbocation rearrangements make sense? Yes? All right.
What does chirality have to do with plus minus again?
Plus minus means it's a racemic mixture. You get the R enantiomer in the same amount as the S enantiomer. How do you make it not a racemic mixture? You have to use a chiral solvent, like BNAP. But that will not come up on the MCAT. All right, so we talked a little bit about SN1. I will now show you guys the reaction that allowed me to best understand all of these trends of organic chemistry, all these trends of resonance. And if you take Orgo of Brooklyn, they emphasize it very heavily, but I don't know if you guys remember it. It's called the Pinacol rearrangement. You guys did a lab, and the lab was called the Pinacol rearrangement. And the whole point of the lab was to teach you the rules of resonance with carbocations. This is the lab. You begin with an alcohol that looks like this. And you place that alcohol in a solution of sulfuric acid, very dilute. And I think a little bit of water as well. Acid and water or water and acid? You guys got to review your lab techniques and safety. All right. So what's going to happen here? Well, the H2O gets protonated by the sulfuric acid, right? So let's say that we have some free hydronium being cool, floating around in this flask. These markers are really nice. I like the little, the pointed tip ones. Thank you. So it's going to protonate either the solvent or, finally, the flask could grow a pair and make the reaction happen, right? And we get protonation of one of those OH sites. And we create a water adduct, which serves as a very good leaving group on that position. And this looks like it's setting up for another SN1 reaction, and you wouldn't be wrong. You absolutely would not be wrong. Because now you basically just have a good leaving group and a solvent, a polar protic solvent. Right? Did you do that thing I asked you guys to do last week or on Tuesday? We'll go over it later. Out of everyone, I expected you to do it.
The thing is, I'm only in Orgo 1, so
Ah.
I don't even know, just in synthesis.
Oh man, that's tough.
So I tried looking at it, I was like, there's no way.
That's tough.
So,
What's up, buddy?
without Google, it's not.
No, that's definitely like an upper level Orgo 2 sort of thing. But we'll go over it later. And I think it'll make a lot of sense to you. Because if you understand the whole leaving group thing, then it's good. Okay. So now we have what's setting up for an SN1 reaction. So what happens in SN1 reaction? We get the formation of the carbocation. I'm going to draw it this way so that I don't need to hunch my back and bend over and everything, because this is important. This is the important part of the reaction. And that basically forms another water, right? So it just adds to the solvent. Okay. Cool. Very good. And now everyone freaks out. What do we do now? We made the water so the water can go back. But if the water goes back, we go back. And then we come back, and we go back, and we come back, and we go back, and we come back, and no one knew what to do. So some people were like, wait, you have sulfuric acid in the flask, which is deprotonated. Why doesn't the sulfuric acid attach there? Sulfuric acid is a very strong acid, which means its conjugate base is very stable. It's not going to want to do that. It's really stable. And we'll get to why later as part of this lecture. So we can't attach the water. And we're not going to do an elimination because it's not warm enough, right? So what's going to happen? The oxygen's going to what? Because you can't resonate because you only have one p orbital here. That's a good point. A lot of us thought that when we looked at this, but that would make a 1, 2, 3 carbon ring. And 3 carbon rings are really explosive.
I think it's metal gold.
Hold that thought.
Okay.
So this is cyclopropane, or sorry, this is cyclopropane, right? And this is propane. If you use this in your barbecues, right? You light a propane tank and then you light a little fire and then you cook food with it, right? Professor Malitsky gave us this example to explain what cyclos are. If you filled a tank with cyclopropane instead of propane, your entire backyard and your entire home would be rubble before you'd even get to light the spark inside of the gas tank. This has a ridiculous amount of intrinsic energy, so you wouldn't want to make a 3-membered ring. So, remember that the molecule would do anything for the carbocation. Well, that's what I thought too when I looked at this. But there's no hydrogens here. It's a methyl shift. So this whole CH3 group detaches and moves. And that is called a CH3 shift. A methyl shift. And that methyl shift creates this molecule. Or this intermediate, I should say. And there's the methyl group that you moved. Right there in the middle. This guy. So we moved. And now alarm bells should be ringing in your head like fucking church. They should be going off like wild. Because, excuse me, what the fuck? We were so okay over here because we had 1, 2, 3 donors. And now we have 1, 2 donors, but we don't just have 2 donors, we have a withdrawing group. Aren't we stealing from the poor? Isn't that what we don't want to do? Isn't stealing from the poor exactly what we don't want to happen? So why is this better than this? Because then you realize that I've been leaving out a small piece of information. That in this whole scheme, they told us to figure out the mechanism, but they gave us the final product. That's the final product. So what you realize is that this carbocation is actually more stable because of one very important overlooked detail. Lone pair resonance. And if you're looking at this wondering, why would oxygen become positive instead of the carbon? Oxygen has a higher electronegativity. You must be forgetting that carbon, when it's positive, doesn't have an octet, but oxygen does. And that, in my way of saying, is oxygen fronting the discomfort for carbon stability. Oxygen is okay being uncomfortable so long as carbon is happy with a full octet. All of you guys get that? All of you guys understand what happened here? We methyl shifted and went to what looked like a less stable position in order to gain resonance. And when we gain the resonance, we create an intermediate which is far more stable than not having an octet, and that intermediate is longer lasting and moves forward in the reaction with a deprotonation and forms this ketone. And when that intermediate forms the ketone, we finish the reaction. That's it. This is called the Pinacol rearrangement. I never wrote out the word rearrangement. I would show an arrow looping on itself. So when I said carbocation rearrangement, I did this. The Pinacol rearrangement. And if you'd like to look it up, you can. And it teaches you everything you need to know about carbocation resonance in chemistry. That donating groups are good, resonance is better, and intermediates can be part of the final product. Intermediates can lead to the final product, right? Even resonance intermediates. And what this tells you, what this specifically tells you, is that even though this is a tertiary carbocation, a secondary carbocation with resonance is still better. And even further than that, everyone thinks a tertiary carbocation is so stable. Professor Militsky ventured to say, and he's looked at so many research papers about this just to make this claim, he ventured to say that even primary resonant carbocations are more stable than tertiary carbocations. So he strongly believed, and I agree with him. I didn't look at the research, but I trust his word. He believed that this was more stable than this. And I trust him. Because how much stability could you really be getting from a donating group, right? Because this is what, a +1 charge? Let's say that each of those donations subtracts 0.1. You're resolving to 0.7. Here it's 50-50, 0.5, across two domains of the molecule. The charge separation, the separation of charges across the entire molecule, that sort of average of the whole molecule, is far more stabilizing than having a localized charge. Remember what we said at the beginning? Resonance is nothing but delocalization of electrons. Delocalized charges are far more stable than localized charges. Why do you think lightning falls out of the fucking sky? Because it's delocalizing. It is spreading itself thin. It is dissipating into the place it wants to go. Hopefully it's not through you. What are those scars called when you get struck by lightning? It starts with an L. No, it starts with an L. There's a specific name for it. Oh, man. I forget. But they look like leaves, and they like radiate like that. Lancaster, or I forget. Something. Someone look it up. It's going to bother me. Just look up scar when hit by lightning or struck by lightning, and it'll come up. It should start with an L. I was going to say Leidenfrost, but Leidenfrost is like this effect that happens when you boil water and it like causes things to float on top of it. You guys ever put a wet pot down on the stove and it kind of floats? Huh? Lichtenberg, yes. Lichtenberg lines or Lichtenberg scars. Have you guys ever put down a wet pot? Like you just washed a pot and you put it down on the stove to cook with, and then the pot kind of floats on the stove and moves around? You've done that before, right? So what's happening is that the pot with the water droplets, the heat is coming into contact with the water droplets, and they're creating gas, and that gas circles up underneath the pot and circles around like this because it gets pushed down by the surface of the pot and then pushed back up because it's a gas, and pushed down, pushed up, pushed down, pushed up, and it creates a layer of gas that the pot just kind of floats over as that water's evaporating. It's called the Leidenfrost effect. I have a lot of random facts inside this head of mine because I watch a lot of shitty YouTube at 2 in the morning. Okay, do you guys think we're good on carbocation resonance? Because that's pretty much as complicated as it could get on the MCAT, right? So now let's take these same rules, because nothing changed. Let's take those same rules and apply them to carbanions and negative charges. Because those are the rules of resonance. And it's not like chemistry is breaking when you change from a carbanion to a carbocation or a carbocation to a carbanion. It's the same rules for different people. MMA fighters, 200-pound MMA fighters, and 95-pound MMA fighters. They fight with the same rules. They're just different structures, different human beings, right? They fight differently, but they play by the same rules. right? Yeah? Okay. So I was going to do one last thing. Oh, before we do, actually, let's do it after. So we talked about carbocation rearrangements, which I told you guys last week to remind me of, but I remembered. One more thing, I'm going to make a note of it. At the end, all the way at the end, we're going to talk about radical resonance. And radical does not mean cool. It means the actual resonance of radicals. It is quite cool, but it also causes cancer. So let's look at this. It is notoriously difficult to create carbocations without using bases. And it's sad, carbanions without using bases. And it's sad because we have to talk about bases in our discussion about carbanions. So it's an infinite sort of loop of trying to define one thing after another. So we're just going to hop into it. So whereas a carbocation has a deficiency of electrons, a carbanion is electron rich. Electron rich. So this is a carbanion. That's a carbanion. And I told you that R groups are donating groups. R group, R group, R group. But what are we doing? Remember I said 2 more rules. Donate to the poor and steal from the rich. Fuck you, Elon. Right? What are we doing here? Are we donating to the poor or the rich? We're donating to the rich. That's a problem. So these R groups are actually destabilizing the carbanion. So this carbanion is less stable than this carbanion is less stable, is less stable than this carbanion is less stable than this carbanion. And that's the absolute opposite of what we see in carbocations. Why? They're playing by the same rules, but they're different characters. You don't want to donate negatives to a negative being. You don't want to take away negatives from a positive being. You want to donate negatives to a positive being and take away negatives from a negative being. And in the same sense, this is less stable than this. Why? Halides and electronegative atoms are withdrawing. Withdraw, slight positive, withdraw. You're pulling back that electron does. You're helping it out. You're helping that guy out. Even better, directly, right? Even better. But that brings up a curious topic on the MCAT, which you probably won't see all too much, unless you're looking at mechanisms and stuff like that, which come up quite rarely, where this actually might not be that bad. Because of what? Lone pair resonance. Because of the fact that that can be stabilized like this. And for my Orgo 2 people, that kind of looks like the reaction that happens when you do a hydrobromination. When you have, and initially you get something like this, right? And then you attack the more stable side, the one that is more unstable as a carbocation but would make the more stable product, which is always that one, right? And then if it's a Br, it attacks there, you get a dibromide, and if it's OH, you attack there, you get an alcohol, right? Orgo people, Orgo 2 people, what's the only thing that you can do with this? if you're starting a synthesis, what's the only thing you can do? Brominate it. Bromination with light, and then what's that going to do? It's going to attach it to the less or more substituted place. More. How do you get it to go less? Peroxides. Roar. Those come up on the MCAT every now and again, where it's like, what would the first step be? Or how did we get here, right? Because from here, you can go anywhere. Yeah, my Orgo 2 people know you can go anywhere from there. Literally anywhere. You can go Grignard, you can go ketone, you can go alcohol, you can go carboxylic acid, you can go anything you want. Good? Okay. So let's look at the resonance of carbanions. It pretty much follows the same rule, where you sketch out this p-orbital map, right? Also, Orgo 2 people, I know you would just do the double jump at first because you can see it, but some people can't. Yet, but they will. Because all the Orgo 2 people are like, why even go through the middle step? It doesn't matter. And then this is going to come up this way, and go there, and come here. Right? I'm going to dial back over here. And we're going to compare. Same thing, different players. And we said before that this was the major contributor, and those were the minor contributors, right? Same rules, different player. Is this still the major contributor? Why? Well, it's getting donated to the same way that guy was. And this is getting donated to the same way that guy is. And this is getting donated to the same way this guy is. But do you want to donate to a negative thing? Do you donate to the rich? No, you don't donate to the rich. So the less you donate, the better. Which means that this is your major contributor, and this is your major contributor, and this is your minor. Whereas here, this is your major, this is your minor, and this is your equally minor. Yeah? Cool. I have to think of so I'm not using notes, as you can see. So I have to think of situations and things that I've encountered throughout my studies of Orgo that helped me. One of them being this. Actually, hold on. Is that, you know what I'm getting at, right? Yeah, and then, but does it go on these two or those two? Because when it comes down, I don't want to show it, but hold on. You could do it both ways, but it's one way is just easier. And that's going to go there. Yeah, okay. That's what I wanted. Ready? I'm going to draw this over here. Can I erase this? Okay, cool. You stay there. because I also want to show you one more thing. And I'm going to show you why carbocation resonance is easier than carbanion resonance. Because the only thing you need to solve a carbanion is one electron push. You don't copy this down. By the way, don't copy this one down. This is just for example. But all you need is one push, and now it's resolved, right? And then this carbanion can either resonate with the fluorine or it can go through the aromatic ring this way. You guys see how that's going to happen, right? Cool. Let's look at the carbanion, because that's what I actually wanted to look at. So the carbanion, it may be hard to see. This is going to come down this way into the p-orbital map that you drew in your head, and you see sp2, 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 right? And that can either break down this way and push the rest of the bonds up, or we can take baby steps. And this is going to resolve to the carbon. And when you're doing resonance, I recommend that you take baby steps. Because if you don't, sometimes you miss stuff. Sometimes you miss stuff, like the fact that this is stabilized by the withdrawing effects of the fluorine. 4.0 electronegativity ain't no joke. And then you go again. And that comes onto this carbon. Always keep track of what carbon you're on. That goes to here. Oop, see, I almost fucked up. And then, dude goes there and this guy goes here. And we're just hopping the ring at this point. I'm counting on the Orgo 2 people to tell me if I fuck up. And then this guy goes back. And why are we going back to the beginning? Well, you'll see that we have now inverted the double bonds in the ring, which is very common of benzene. It does this all the time, every single day. That's why it's aromatic. That's what aromaticity is. And if we were to label major and minor contributors, where would they be? That's such a tough question. What would our major contributor be? I'm going to say, hold on, A, B, C, D, and E. There's one major contributor. Is it A? Who thinks it's B? Who thinks it's C? Who thinks it's D? And who thinks it's E? You think it's B. A lot of people think it's B. Because it is B. Because the fluorine, like I said, pulls away that electron density. It helps to stabilize. But after B, we then need to look at donating effects, withdrawing effects, et cetera, et cetera. This gets a little more complicated. But I'll tell you right now, it's probably going to be this guy. Because the fluorine withdraws from here, which withdraws from there, which withdraws from there, and this fluorine withdraws like that. So you get a little bit of withdrawing rather than being so far away from the fluorines over here. So you can see that negative ions, carbanions, like to be closer to electronegative atoms. Correct? Yeah? Very good. So that's carbanion resonance. Now, we've spoken about resonance, and that can get us to begin to talk. So we talked about, what did we talk about in Gen Chem? Does anyone remember what chapter 2 of Gen Chem was? What the name of the chapter was? Periodic table. and periodicity. And we had this whole discussion about electronegativity and electron affinity and size and ion size and this and that and blah, 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 and like everything. We talked about everything, right? So we did that. And then we did acids, bases later in that book. And then we did acids, bases last week, or on Tuesday, right? So we did acids, bases. And then we just did resonance. And we talked about the inductive effect and blah, blah, blah. And hybridization, we did our hybridization stuff. And we talked about p-orbitals, and we did this and that. All of that culminates to one discussion. Base stability. Otherwise known as leaving group stability, because leaving groups are just conjugate bases. Specifically, you can write conjugate base stability, because that's really what it's all about. That's what orgo is all about, these reactions, addition reactions, substitution reactions, TCAIs, carboxylic acid derivatives. It's all about what? My guy nodding his head in the middle, he knows, conjugate bases. It's all about conjugate bases. You're an orgo guy, aren't you? So was I. Orgo is a lot of fun if you understand it. There are 5 properties that stabilize a conjugate base. Thank you, Professor Militsky. I cannot thank him enough. The size of the atom that holds the charge, the electronegativity of the atom that holds the charge, resonance, or lack thereof, hybridization, or lack thereof, and inductive effects. For all of the people back home, I don't have enough room on this board, and I don't have a wide camera. Go back to my video, the one right before this one, which is chapter 3 and 4, organic chemistry, and copy down the pKa table that's at the end of that video. For everyone else, I'm putting it on the board here. Okay? HF, H3O plus. What was after H3O? No, sorry. I am forgetting already. H3O plus, HF, H2CO3, HSR, NH4. Hold on. I don't know if I gave you this one last time. HCN, is that on yours? Yeah? HCN. And then we have H2O, and then ROH, and then acetylide, and then we have NH3, and then we have this. -9, -7, -5, 0, 3, 6.4, 8, 6.2, 9.4, 10, 15.7, 16 to 18, 25, 38, 40, 50. And I said that as the pKa goes up, the stability of the acid goes down. This is your pKa table. So we would say, as the pKa goes up, the stability of the conjugate base goes down. So we would say that the most stable conjugate bases are up here by HI, and the least stable conjugate bases are down here by ethane, correct? And when we talk about the pKa, we talk about the pKa of the first proton that is abstracted off of that position. So let's do some comparisons. Oh, I know what's missing from this table, and it's a really big one. Carboxylic acids. Roughly 4. 3 to 4. I think it's 4. I cannot believe I left that out. Holy shit. Right? So let's do some digging, shall we? So let's say that we have a reaction between this and this. What's going to protonate what? What's the stronger acid based on the table? Just based on the table.
The SH is a stronger.
Yeah, so we're going to get that. That's what we're going to get if they reacted. But classically, you won't be shown it like this. You're going to be shown it like this. Oops. Why did I look back over there? You're going to be shown it like this. And you're going to be asked, delta G of the forward reaction. And your three choices, four choices. Less than 0, greater than 0, equal to 0, cannot determine with the given information. I'll give you a hint. It's not D. Oh, Professor Molitsky used to do that. Dude, I'm just turning into him. Whenever he used to cross stuff across the board, he'd go like this and he'd just like walk by the board like that. If you guys can't tell, I have a lot of love for him. Okay, so before we answer, let's talk about the thermodynamics of this process. What are we talking about? We're talking about conjugate base stability. Here is an acid, and I'm going to start using the other colors now, because we need to display two different reactions. Here's an acid and its conjugate base. And here is another acid in a different reaction, and here is its conjugate base. And we have to ask ourselves, which of the conjugate bases is more conjugate base, is cooler, is more fetch? So which one's more stable, right? Sulfur. And a lot of people will say this, I don't know what to call this. It's a thiolate, right? But this thiolate is more stable than that ethoxide, right? Because of the fact that HSR has a pK of 8 and ROH has a pK of 16, 18. But what does that mean? Like, why? Why is it more stable? Well, let's take a look at the 5 things that stabilize a conjugate base. What does this have going for it that this doesn't? Huh? It's bigger. It's bigger. But the electronegativity here is greater. And there's no inductive effects on either side. And the hybridization is the same. And there's no resonance. But remember what I said way back in the Gen Chem chapter, chapter 2. If you have to rewatch that video, I would. It's essential to your understanding of conjugate bases. Do you remember what I said? That electrons, they're like tiny little infants. They're like these, what time is it?
7:20.
Beautiful. They're like these little kids, right? They want to run around and scramble and do whatever the fuck they want to do. So if you confine them to a space this big, or if you give them this big of a playground, what are they going to prefer? They're going to prefer that. So size is more important there, and the conjugate base there is more stable. Yeah? Because this is a 3p element, and this is a 2p element. So that's size out of the way. So the delta G of the forward reaction is what? Negative or positive? Negative. Very good. Size. My Orgo 2 people should be screaming. Screaming. Which way does it go, left or right? Come on, guys. Orgo 2 people. We just talked about how ridiculously strong that is. It's going to be this guy. For what? What's bigger? What's bigger? B, C, N, O, F. As we go down a period, we decrease in size. So nitrogen is actually slightly larger, but slightly. So it's not that much more room. We're not talking about difference between periods. So size matters between periods, but electronegativity matters within a period or between groups. So group 16 versus 15, the electronegativity is what matters. And that's why this is more stable. And the delta G of the forward reaction would be positive. That's how it's going to be presented to you on the MCAT. Delta G of the forward reaction, blah, 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 blah. Now on to why we talked about resonance in the first place. Oxygen, oxygen, same electronegativity, same size. However, what does this have going for it? Resonance. Very good. It splits up its negative charge amongst two species on the same molecule. And that, what does that contribute? It goes from 16 to 18 to 4. How much of a drop is that? A lot of people say, what? Let's say it's 16 minus 4, that's 12. They're like, oh, 12x. No. pH scales and pKa scales are logarithmic. That is a 10 to the 12th stability, meaning that this guy is how many times more acidic than ethanol? Ethanoic acid is how many times more acidic than ethanol? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That many times more acidic than ethanol. Which is why if you drink vinegar, it'll taste acidic, but if you drink ethanol, you might crash your car. But what does your body do with ethanol? Do you guys know? Turns it into acetic acid. Your body takes ethanol, and this is why we do redox reactions, because I'll teach you guys this in biochem. It takes ethanol, and it turns it into acetaldehyde, and then it turns that acetaldehyde into ethanoic acid. Oxidation, oxidation. And do you guys know Asian glow? How when people of Eastern Asian descent drink, they turn red in the face? It's because they lack this enzyme. And acetaldehyde is really toxic to your body, so it causes them to get flushed because of the cytokine release. This is inflammatory. This is what gives you a hangover. So if you drink a lot of water and you dilute this and you piss it out of your system the night before you wake up, you won't get a hangover.
Is there a way to build up more of that enzyme?
I don't know. Maybe you should find out. But mind you, if you build up more of that enzyme, you're drunk for less time. Pretty much. Resonance, we're good? Yeah? Cool. Hybridization is very, very, very simply shown in two of those things. Or just, you'll see it like this. What's more stable? What's the more stable conjugate base? Well, we've got this guy at what? A 25, and this guy at a 40, right? And we always go towards the conjugate base of the more strong acid. So why is this guy more stable than this guy? Let's take a look. Versus this is sp hybridized, right? Remember my trick. Whatever you're not using, what is that? Free p orbitals. P orbital, p orbital. Those are both contributing to the 2 pi bonds with the adjacent carbon, right? But what else are they doing? P orbitals are louder. Electronegative. Every time I say it, p orbitals are electronegative. They are literally pulling those electrons closer to the structure, stopping them from interacting with their surroundings. And when the electrons interact with their surroundings less, you stabilize the conjugate base. You have 2 p orbitals there. How many do you have here? 1, because that's sp2. And if you look, if you're not using it, it's free. It's only 1. That's 2. There you go. Conjugate base stabilization by hybridization. And lastly, everyone's favorite, and the MCAT's favorite, because you're going to get a question like this, inductive effects. The question looks like this. Which of the following is the strongest acid? This guy, right? Why? Well, let's deprotonate all of these and look at the conjugate bases. Same thing, right? Get used to seeing them in different configurations. They're not always going to show it to you upright. This guy, all of them have resonance going for them. The size is the same. The hybridization is the same. The electronegativity is the same. Everything else is the same. Now we got to look at inductive effects. This guy, the R group is donating into the carboxylate. Why am I saying the carboxylate? Because it's resonating. That's the whole electron density right there. Here you got the donating, but you also have the F really, really withdrawing here, right? And over here, you got donation, and you got a little bit of withdrawal, but it's like 3 steps away, right? So the most withdrawal is going to happen over here, and that's why this guy's the strongest acid. Does that make sense to even the people taking Orgo 1? Very good. Good, good, good. I forget when you guys do things. It's been 4 years. It's been a good 4 years. 3.5. I'm not that old. Oh God, I was 19 when I took Orgo. You guys know how old I am now? 23. So those are the 5 factors that stabilize conjugate bases. And now you'll be able to tell, right, on the MCAT, when someone says which of these, I don't want to do chirality right now. When someone says which of these happens faster, right? When someone says which of those reactions, like which of those leaving groups leaves faster, you'll be able to tell me. Because when this leaves, it's going to make Br minus, and when this leaves, it's going to make I minus, and even without the pKa table, Br and I, F, Cl, Br, I, going down the row, the size increases, and if iodine is larger than Br, it's more stable, and that's going to leave faster. That's it. Guys, I really wish I could go through the whole carboxylic acid derivative thing with you. This took a little longer than expected, and I have to go study for my exam. It's on Monday. So we'll do that next time. I'm not going to be here on Tuesday. I'll see you on Thursday. So on Thursday, we'll have a full lecture, 6 to 9 p.m. like we did before. We'll go over the carboxylic acid derivative stuff, and we'll circle back on chapters 1 and 2 of organic chemistry and rename stuff. But before you leave, radical resonance. Have you guys ever heard of antioxidants? I'm chock full of them because I'm brown. I be eating ginger and turmeric and garlic all over the place. I'm chock full of antioxidants, right? Antioxidants, what are oxidants? They're things in your body that can oxidize, right? And the biggest ones are ones that we're able to get from oxygen. And oxygen in our body can turn into a plethora of things. One of the most important ones being a reactive oxygen species. We talked about this back in bio, chapter 1. The cell peroxisomes, right? Make what? They make hydroxide radical. And in your body, you need a way to stabilize that so that it doesn't go around and bend your fucking DNA over and give you cancer. You need a way to do that. Why should you guys not suntan? I don't care how pale you are. It's because you're making that in your body using the light. You're quite literally giving yourself cancer. Don't tan. I have melanin. I do not tan. I'm this color all year round. So, one antioxidant in your body is what? Tyrosine. What is tyrosine? It's an amino acid whose structure looks like this. It is phenylalanine with an OH group. So it is a phenol on top of alanine. Right? Not phenyl on top of alanine, because phenyl means benzene ring, but a phenol on top of alanine. Specifically a paraphenyl. Right? Orthometapara. And when a hydroxide radical comes into contact with tyrosine, tyrosine is able to couple the radical. A 1 electron donation from the proton and a 1 electron donation this way. Those are called fish hook arrows. 1 electron. Double-headed arrows are 2 electrons. Okay? That's going to create H2O from the hydroxide radical, which is now stable as water, and we're going to create a tyrosine radical. Always draw your radical electron a little bigger so that no one mistakes it. You guys ready to see the magic? This guy's ready. Fish hook arrow down, fish hook arrow in, fish hook arrow out. That is radical resonance, where the radical disperses itself throughout the benzene ring. And I'm going to take this, and I'm going to say R, okay? Because I'm not going to keep drawing it. So when it disperses itself throughout the benzene ring, you get R, and then you get double bond to the O because you made it with that 1 radical electron. The radical goes here, and we go here and here. This comes down, down, and in. More resonance. R. Double bond O. Orgo 2 people. If this was not a radical, what would this structure be called? It's called a quinone.
Yes.
Down, down, and in. More resonance. R. And yes, I know I'm changing the orientation of the molecule a lot. That is on purpose. And then up, down, and in. And we come all the way back to the oxygen. And we have flipped the orientation of the double bonds. That is how tyrosine stabilizes the radical. It spins it around and around and around and around and around the benzene ring until tyrosine radical couples with another tyrosine radical and makes so the radical here couples with look, everyone look, everyone couple, and you make a dityrosine compound, which can be urinated out of the body. So we started with a hydroxide radical, or 2, and we had 2 tyrosines, which captured them, stabilized them inside of their resonance, coupled to one another, and will subsequently be urinated out of the body. Or we will learn in biochem that glutathione, which is a radical scavenger, will come, reduce this, become oxidized. Oxidized glutathione forms a cysteine bridge, a disulfide bond, which will get reduced by NADPH, and it cycles. We will learn about glutathione and radical scavenging in ways other than this when we talk about biochemistry. But if you have taken biochemistry, you have an interest in biochemistry, glutathione is a protein which has a cysteine residue inside of it. And that cysteine residue sees this radical, right, reduces it with one of its own electrons, forms a cysteine radical, couples with another cysteine radical from another glutathione, and forms a disulfide bridge between the 2 glutathiones. That disulfide bridge can be reduced by NADPH, forming NADP+, which cycles back into the pentose phosphate pathway and regenerates NADPH. If you followed that, you're quite good at biochemistry. Isn't it? All right, and if you followed that back home, congratulations. And if you followed all of this back home, congratulations. This was one of the tougher lectures that I've given, but I hope that it gave you a little bit more of a background of how base stability and resonance works before we move forward in organic chemistry, because this will be very important when we do the aldol, Claisen, Michael, and Dieckmann condensations. Understood? Have a great night. I'll see you guys next time. Please go home.